Hello Internet, my name is Quinn and this is Blondihacks. Working on my locomotive this week, continuing with the cylinder lubrication system, I'm going to build the oil pump. And before the end of this video, we'll find out if it does pump oil or if I just made tiny adorable yard art. So let's go. Last time we finished this oil tank, perhaps the less said about it the better, but I do need to point out that it has these holes on the back and the bottom. The oil pump itself is L-shaped and it sits between these two holes. So let's get started making that. The pump body has a hexagonal profile in the middle of it, so we'll start with this chunk of hex bar stock over here on the lathe. This pump is very similar to the other two pumps that I've made for this locomotive. However, it is smaller than the other two by quite a bit, so we're going to be doing everything kind of miniaturized. And it is quite a different shape. It's all kind of squished into a little cylinder so that it can fit inside that oil tank. It's kind of a miniaturization of an already miniaturized part, which is going to create some interesting fresh challenges. I didn't expect this part to be very exciting because it's the same as the other two pumps. I almost didn't even bother filming this part, but it turned out to be quite a bit more interesting than I thought, so I'm glad I did. A little test fit there to make sure that the body of the pump is going to fit through the bottom of the oil tank. And then I turn down the upper section of it. The bottom base of it is going to be threaded into the bottom of the oil tank with a banjo fitting. That's how it gets held into the tank. And then this top section here is turned down so that the banjo nut can slide down over the whole thing. Speaking of banjo fittings, we're going to create that now, or at least one half of it. There's a groove at the base of this thread that sits in the bottom of the oil tank, and there's going to be some cross holes drilled through that, and that's where the pump inlet is effectively. This will all make sense in a minute. So I'll put those threads down there now over top of the body of the pump. Now I can get started on the internal features. I'll start with the bore for the piston of the pump. Now this is a basic piston pump like the other two that we made. Interestingly, however, this one only has a single check valve, and that's because it's pumping very, very viscous oil. The other two, of course, are pumping water. Now with viscous oil, you can do a little trick. As long as the force required to compress the spring on the output check valve is a little bit lower than the force required to push that oil back out through the inlet, then the pump can draw oil in, and then when it goes to push it back out again, it'll take the path of slightly less resistance out through the outlet check valve. This will make sense more in a minute, but it's a pretty neat idea that simplifies this pump quite a bit. This piston bore is a simple reaming job. It doesn't have to be especially concentric with anything. Now I started with that end because I'm going to need to flip it around and do a second set of operations, and I can hold on to the smooth diameter at that end with a collet. And I lopped off the extra hex bar stock, and now I can start working on these other dimensions on the other end. I could have also used the forejaw here if concentricity was absolutely critical, but with this collet chuck it'll be close enough. Now I can face that hex section down to final width now. This feature is a good excuse to use this interchangeable anvil micrometer that a viewer sent me several years ago. This thing can get into tighter spaces than a normal one, and every so often it's a real lifesaver. Not that this dimension is so critical that it needs a micrometer, but you know, it's a good chance to use the toys. I'm ready to cut the valve seat now, but here's where things get a little interesting. Because this pump is smaller than the other two I've made, my normal valve seat cutting tool on the left is too big. I need to make an identical tool that's a little smaller, shown on the right. So let's pretend I haven't done that yet and go back in time and go over to the D-bit grinder. This is a split carbide blank. I have a few of these in stock, and they save you a whole bunch of work when you need to make a D-bit on the D-bit grinder. These things are getting increasingly hard to get, unfortunately. They used to be cheap and plentiful. Now I gotta really hunt for them, and they're expensive. But these split blanks are a real time saver because 80% of the work in making a single flute or D-bit cutter is splitting the stock, grinding away half of the cylinder before you start. So these split blanks are really nice. I guess they're less common now because D-bit grinders are kind of falling out of fashion. People don't use them much anymore, but it's a shame because they are sure nice. So for now, I'm running through the remaining stock of split blanks that I have, and after that I'm going to have to start using center drills and old end mills and doing the splitting myself. I start by necking down the area that I'm going to need to get the reach that I'm going to need. I calculated from the drawing how much reach this tool is going to need to get down to the valve seat. which turned out to be less than the actual split area on the blank, but that's fine. So I'm going to neck that down to be a close running fit in the smooth bore that is above the valve seat, because that's going to support this tool as it's cutting the seat. Now I can swing it around to put the 15-degree valve seat angle on the end. I also lean the workhead forward 10 degrees with the tool upside down, creating a compound angle, and that's going to give me the end clearance on the end of the tool. So the end of this tool is what does the cutting, not the side of it, which is good for me because it makes it a very easy tool to grind. If you were making something like a single flute end mill, which cuts on the side and the end, then you have to do additional clearancing on the side edge of the tool, and that's actually one of the things that the D-bit grinder is especially good at. That's kind of its superpower, is that it can create this kind of decreasing radius clearance on the side cutting edge of a tool. I've covered that in my video on how to use a D-bit grinder, but luckily we don't need to get to that complexity here. We just need the end clearance to cut on the end of this tool. And that came out pretty nice, I think. Now I want to pre-drill for that tool, and to do that I'm going to set the end of the drill on a feeler gauge. Then I can zero my quill DRO there, advance by the thickness of the gauge, re-zero, and now I know the end of that drill is right on the end of my part, and I can pre-drill to an accurate depth for that valve seat. Fortunately, the design of this part has a few thousandths of wiggle room here and there for where this valve seat ends up, but I want to get as close as I can to nominal anyway. This hole is drilled, not reamed, so I actually started with a slightly undersized drill, just in case the drill cut over size, as they often do, and I'll test fit now with my valve seat cutter. It doesn't quite go in there, so the drill cut dead nuts on size, which sometimes they do that too. So that's a good thing though, and now I can go up to the nominal size drill and go in again, and I know I'm going to end up with an accurate hole because the previous drill has left so little work for this one to do that it's going to cut on size. The less work you make a drill do, the more accurately it cuts to its nominal size, assuming it's also a high quality drill that's been ground on size, which, you know, some of them are better than others, of course. Second test fit then with my valve seat cutter, and that is now an excellent fit in there. So that tool will be well supported while it does its work in the bottom of that hole. So now I'm going to set the distance again for my valve seat cutting tool, make sure the end of that valve seat is in the correct place. And the end of this cutting tool is going to clear away the drill cone that was left, the 118-degree negative cone, and it's going to clear that away and then leave a 15-degree positive cone in the bottom of this hole. And that positive cone later becomes the valve seat, as you've seen on the other pumps that I've built in this series. And right about where I expected to on the quill DRO, I saw chips, so that's a good sign. I did something right. These internal features are always a little exciting because you're flying on instruments, as it were. You really don't know what's going on in there. You just have to hope you did all the math right and ground all your tools correctly. I also need a few threads in there for a sealing cap, so run a tap in there quick. The tool pressure of this tap was a little bit too high for the not so great grip from my aluminum adapter collet there. Luckily it has a hex profile on it, so I threw a wrench on there to keep it from spinning. I haven't gronked down on that super hard because this is a hollow brass tube, and also the grip I get from these aluminum adapter collets is not spectacular, but it's usually good enough, except for the occasional high tool pressure thing like a tap. Then, much like you've seen on the other pumps, we put a counter bore at the end of that thread to seal on a tapered cap that's going to go in the end here. This counter bore forms a sharp 90-degree corner that gets deformed when we crank down with the tapered plug that goes in there, and that forms a seal, more or less. Sometimes it needs some Loctite 545, as you've seen. As is tradition then, here's the look inside to see what we did. You can see we created the valve seat at the bottom, and then there's a smooth bore where the bearing ball is going to ride that forms the actual check valve, and then above that are the threads for the sealing cap, and then above that is the counter bore that seals. I can fish this out of here now. We're done with the lathe for the moment, and we need to do the rest of the features for the pump inlet, which is just below those threads, as you might recall. So I'm going to go over to the mill and set up to do those. There's 4 cross holes that meet up with the center bore of the pump body. I'm going to edge find on the collet block itself to center up on that part, which is decent enough. There's some sources of error here, of course. I'm assuming that the collet is concentric with the block, which is concentric with my adapter, which is concentric with the part. But assuming all that is true, then this is close enough for cross drilling anyway. I drilled 2 pairs of holes straight across, indexing 90 degrees between them, and forgot to press record, but there's the final result. When the piston on the pump lifts up, it's going to draw oil in through those little cross holes into the center passage, and then when the piston comes back down, it's going to push it out the bottom of the pump. Let's give it somewhere to go now by creating the outlet of the pump. I turned this little stub that's going to get soldered onto the side of the pump. Turned this out of some brass. Similar to how you saw me do the previous pump on this series, I turned a little threaded stud with a smaller diameter on the back of it that allows me to register it in the body of the pump and solder the two together. This is an identical part essentially to the outlet on the Axle water pump, but just smaller. Everything on this pump is smaller. So there's a through hole and then a little counter bore, and then I use a grooving tool to put a little registration diameter behind the thread that's going to register on the body of the pump. And then since I'm here with the grooving tool, I also use the grooving tool to part this thing off. That registration diameter is calculated to be a close fit on a drill that I happen to have that will create the diameter on the body of the pump without going too deep or without going too wide and blowing out the sides of the body. Now over on the body of the pump, I'm going to register it horizontally using an adjustable parallel so I can get it aligned the way I want in the collet block. And that's going to allow me to then center drill and drill the registration diameter that I talked about. And I'm not going through with this drill. I'm going just deep enough to where the full body of the drill has engaged. So I have the full diameter. And then that little stud that I turned on the back of this teeny tiny threaded outlet can sit down in there, register nicely in there. And that's going to hold that sufficiently in place for silver soldering. Let's do that then now. I'll get some flux on there. Everything's been pickled, of course. I'm going to put the little outlet boss on there, and I'm going to hold the whole thing level with a shim. This metal shim is actually titanium. This is from New Concepts. New as in I knew it, not new as in novel, K-N-E-W. And they sell these titanium strips for jewelry soldering fixturing. You can bend them into all different shapes. I'm just using it as a shim here. This is the lamest possible use, but I'm still getting the hang of these things and figuring out use cases for them for me. But they seem like a nice thing. The reason they're titanium is that titanium can, of course, take the heat and it doesn't stick to silver solder. So you can get it in close to your joints and hold things in place. So I touched a little silver solder in there. Didn't look like much happened right there, but that was it. That's all it needed. It's a very small joint. Repickle then, a little bit of cleanup, and I can go back over to the mill because we now need to drill that boss through into the center passage to complete the outlet. I had already pre-drilled part of the passage that acts as a drill guide essentially, and thus it's easy to drill it straight through and complete the connection. That should be it then for this pump body. That seems to have gone reasonably well. We won't know for sure if it works until we get a few more parts made, but I'm pretty pleased with how that's gone so far. Now the next piece to make is the banjo nut that goes over those little cross holes that form the pump inlet. Let's get back over to the lathe with some more hex bar stock and see if we can crank out a banjo nut. This is a neat little part actually. I like these little kind of one-off specialty machine hardware type parts that the kind of thing that you wouldn't be able to find at a hardware store, but are the secret to these little mechanisms working. These are always fun parts to make. So start with a tap drill size all the way through the part, and then a counter bore at the bottom of the part. This is a larger diameter than the body of the pump, so it forms kind of a cavity, and that's, again, going to be the oil inlet. And then once that's done, then I tap the threads at the back that we previously pre-drilled, create the threads of the nut through the counter bore, and that's going to make this into an actual nut. Next, I'm going to turn a diameter on the inside of the part, and this is just going to be for fixturing for the next step. Hex bar stock is difficult to hang on to for the type of setup that I'm going to need to do next, so I'm going to create a temporary diameter to empower myself to be able to do that. Once in a blue moon, I do actually plan ahead like you really should with everything in machining. Break those corners, of course, while we're here, because chamfers are what separate us from the animals. Yahtzee. Back over to the mill now with a hex collet block, except I want the flats on the part to be oriented flat with the mill, not pointy side up like the hex collet block is. So I want to clock this 30 degrees out of phase with the collet block. So I'll again use an adjustable parallel to do that. Just doing this by feel on the parallel is close enough. We don't have to indicate this in. It's not that critical. But this is going to allow me to then index all 6 sides, but end up with the flat sides being drilled through. In fact, I only have to do this 3 times. I center drill 3 of the faces, and then I can cross drill all the way across from those 3 starting points to get all 6 cross holes. And then these 6 cross holes, as I said, will become the outer layer of oil inlet for the pump. The oil will get sucked in through these holes, end up inside the banjo fitting where those 4 cross holes were, and then get sucked into the body of the pump. And again, the resistance to suction of these small holes on the extremely viscous oil is presumably calculated by Kozo to be slightly higher than the spring force on the output check valve, and so we don't need an input check valve on this pump. Then back over to the lathe to face that temporary boss off the back. I gripped it kind of lightly in the chuck jaws so I don't damage the surface of the finished part, and I took light cuts to face it all the way down. This nut is also what fixes the pump body into the oil tank. It threads over the body of the pump and clamps it into the bottom surface of the tank. This little nut is doing a number of jobs. It's always pleasing mechanical design when you have components that do more than one job. That's looking pretty good right there. Now I can quickly knock out the sealing plug that goes in the bottom of this pump to hold the check valve in place. And that's once more with some hex bar stock, a little smaller dimension this time. I'm going to turn this whole thing with a chamfering tool because this plug has to end up with a 45-degree taper at the top of it that does the sealing. And then drill a little pocket in the bottom, which retains the spring for the output check valve. And Yahtzee. I'll do a little test fit now to see if that plug goes in there. There's not a lot of threads on that plug. The drawing specified a finer pitch thread than I used. I didn't have the correct tap for that, but I had a slightly coarser one, so I think it'll be fine. That looks like that's going to work. Next, I'll form the valve seat. The stainless steel bearing ball goes in there, and then I've got a brass drift with a concave surface on the end of it. That goes down on top of the ball, and then a medium spice whack will convert that cone into a valve seat. This is a process you've seen lots so far in this project. And then the obligatory suck and blow test. Off camera I made the actual piston. It's not worth filming really. It was a simple stainless steel ground rod that I used some emery to sand down to a sub 5/10 fit on that bore. Then at the outlet there's a little stainless steel spring. That was made earlier when I made a bunch of stainless steel springs. You saw that in this project. If you've been watching this whole playlist, I did that on the lathe as well. That thread's in there. I don't think this spring actually has to be stainless. The drawing specifies it as such, but I mean, it's going to spend its life literally bathed in oil, so I think regular spring steel would be fine. Anyway, pump threads in through the bottom of the tank, and the banjo nut goes down on top, and I'll use a deep socket to snug that down. This doesn't have to be very tight because it's not very difficult to seal the oil in there. This oil is so thick, it's not going anywhere. Remember, this isn't pressurized oil, so it's not like on your car where seals all have to be perfect or they leak oil. This is all unpressurized oil, which is extremely easy to contain. Moment of truth, let's get some oil in that tank and see if it pumps. And a couple of strokes, so it primed. Look at that, it's moving oil. It took me a minute to figure out where the correct range of motion for the piston is. It's a lot lower down than I thought, so I had to get out some pliers, but once I did that, whoa, look at that thing go. That is really shifting oil every single stroke. That's honestly working super well. I'm very pleased with that. For such a simple little pump, it's surprising how well it works, honestly. Now, obviously, this is way more oil than the locomotive would ever use. You'll see how we're going to be regulating the oil flow later in this series, but for now, that pump is pumping like a champ. And I could not be happier about that, honestly. Everything went really well on this part of the build. It was a refreshing change from how much of a disaster the tank was, but building a pump went great, and I couldn't be happier with that. This is such a simple thing. It's only 3 parts, and it works so well. It's really quite a nice design. Well, thank you so much for watching. Thanks to my patrons for making this happen every single week, and I will see you next time.